In this video, I'd like to talk about PoseGPT chatting about 3D human pose that is submitted to arXiv on November 30, 2023. And the paper is about adding the ability to large language models to output 3D human pose in addition to the text. But before talking about this paper, let's just give you a quick background about it. When us as humans see a picture like this, we can ask ourselves questions like, what are these children doing? Or how does the girl with the cyan hoodie and pink pants play if she's tired? But to answer these type of questions, we need to have the ability to interpret the images. But in addition, we also need to have some understanding of world knowledge. Like we need to have this ability to know what happens if a person becomes tired. But on the other hand, when we look at current 3D human pose estimation models, we see that some of them receive an input image, and then they try to find the person, and then they segment it, and then they train a neural network to output 3D human pose parameters represented by this simple model. And in another line of research, they receive input frames of the video as the input, used an off-the-shelf 2D estimator to estimate the 2D locations, and then they train a neural network to lift these 2D poses to 3D pose. But the issue of these models is that they have no contextual information. So they do not care about anything happens in the background. And if I have at inference time, let's say an image with multiple persons, and if I ask them to only give me the 3D human pose of a person near the bookshelf, these models fail to understand what is the bookshelf, because they are only trained to understand humans and nothing more. And we also have text-driven pose generation, like MotionGPT paper, Human Motion as a Foreign Language, that we can give them a prompt like, can you generate a motion that a person kneeling on the ground gets up? And they successfully can generate these type of motions. But the issue that these models have is that they are trained on a data sets like AMAS, that they have a limited range of human behavior, emotion, and interaction. So at inference time, if we ask them to generate a type of motion that they haven't seen it in training, they fail to understand, and as a result, they cannot generate something that we actually need. But multimodal LLMs have seen significant progress recently. Like we have this Lisa model that we can give it an image and ask like which part of this picture looks strange, and ask them just output a segmentation mask. So the model has the understanding to interpret the image, and also based off the world knowledge it has, it can segment the horns because it already knows that dogs do not have any horns. Or we have visual instruction tuning paper from NeurIPS 2023 that they present Lava model, and Lava receives an image and we can ask them questions like what is unusual about this image. And this model is capable of outputting text, like it can understand what is strange, so they explain it and they also give you the reason why it is unusual. Or we can also have NextGPT that we can have transition from any modality to any modality, like from text and image to text, or audio or video. But the existing LLMs do not have an ability to interpret 3D human pose. So a question we can ask ourselves is that, what do they already understand about 3D pose, and how we can teach them to more know about this 3D human pose? And the answer is this PoseGPT paper. Then they use an LLM that they receive text and image, and as the output they have text, but in addition they also have some human pose token that we can project it and use a simple model to render it, and as the output we have a 3D human pose. To give you an example, we can have something like this. Like I can ask them to, for example, I want to build strength in my arms and core. And also I want to improve my sense of balance and just recommend me some yoga pose. And the model can, based on its world knowledge, give us something like plank would be a good thing. And I can say I don't like it, recommend something more advanced, and they can recommend handstand. But if I don't understand what handstand is, Now I have the ability to ask it like, can you give me simple pose of this one? And then they generate it. Something that we do not have it in other large language models. Or as another example, I can give it an image and ask it to describe the person's pose, and then the model has the ability to estimate it. Or even more complex scenario, I can give it an image with multiple persons in it and ask it to estimate the pose for a person like having a green shirt. And once it does it, I can give it questions that are more complex, like what might his body pose be when he finishes getting his haircut. So it already has to know what happens when we finish our haircut, obviously when we stand up and we want to pay. So it just generated. But an issue that PoseGPT has is that it cannot outperform specialized methods like the ones specifically designed for 2D human pose estimation from a single image or pose generation from text descriptions. But LLMs, once they know how to interpret simple poses, they can add this word knowledge they already know to reason about these human poses without extra data or training. And because of that, these authors have proposed new benchmarking. One of it is speculative pose generation, or SPG, that we can ask it questions like how would the person's pose change if they were tired? Something that the other models cannot understand. But this model, since it has some understanding of what happens when people become tired, and now it has the ability to estimate and generate poses, now it can give us some reasonable outputs. And another benchmark is reasoning-based pose estimation, or RPE, that we can ask it questions like, what are the poses of all people wearing glasses? So the model, in addition of paying attention to people, now it can pay attention to the background and some facial or behaviors specific to the person and give it a specific output belonging to that person of interest. So enough of this introduction. Now let's just talk about the architecture. So the model as the input receives either text or image, but this image could be optional. And as the output, it generates text. But in case that for the text as the input, I explicitly tell it to give me the simple pose, then in addition to the text, it has to also output simple pose. And what about the LLM that they are using? So for the LLM, they are using Lava version 1.5 that has 13 billion parameters. And Lava is a multimodal language model that in addition to the text, it also understands the image that I already gave you some examples in the introduction. So Lava specifically uses clip to understand these images and encode them, and Vicuna 13 billion for understanding the text. And mathematically speaking, we can represent this LLM as a function f with parameters phi that they are trainable. And as the input, we have some text like, can you give the simple pose of this person? And also have some image like this image of a person in a specific pose. And the output, the model has to give something like the simple pose is this pose token. And mathematically speaking, we can represent the text input as xq, the image input as xv, and the output text as yt. And then we can represent this function f as this thing, that yt equals this function f that receives xq and xv. And for the scenarios that we don't have any images, we can just say yt equals f that receives only xq. And how can we interpret this output? We can say for each of these words, we have some embeddings. Like for the de, we have this thing. For simple, we have this thing, and so on. We can consider the set of all these embeddings as HT. But among all these tokens, what we care more is the last one, which is belonging to this pose token. And let's just represent it as HPose. So once we have this embedding HPose, we can use another function g that has parameters small theta. It could be just some MLP, and the output is capital theta, which is the parameters that simple model expects as pose. But if you already know how simple model works, you know that in addition to pose, we need to have shape or beta parameters. But for these beta parameters, for the sake of simplicity, they set it to be 0, meaning that for all the outputs, regardless of being fat or skinny in the image, they always estimate it as a person with the average shape. So these theta and beta, which is 0, they are going into a simple model, and then this simple model render this person, and we have an output like this. So a question is, how can we train this model? Well, for the clip that we have in this vision encoder and projection, we just keep the parameters frozen and we don't even train it. But for the Vicuna 13 billion, we fine-tune it using LoRA. And if you don't know LoRA, it's a parameter efficient fine-tuning, which I'm about to tell it if you don't know in a bit. But once we train this, we need to also have a loss function. So for the loss function, they use cross entropy between the embeddings yt hat of our ground truth and yt that the model outputs. But for the pose, if in case that we output some pose, we have some L1 loss between the parameters of the ground truth and the estimated parameters. And we also have these two lambdas that they are some hyperparameters. Okay, so go back to LoRA if you don't know what LoRA is. LoRA stands for low rank adaptation, and it is just a method used for fine-tuning large language models. So theoretically speaking, let's just say we have an input vector x and some output vector h, that they are both d-dimensional vector. The simplest way to train a neural network is just a simple weight matrix, W, from d-dimensional to d-dimensional, and we just pre-train it for some task. And we can represent this h as W times x. But in LoRA says, instead of fine-tuning the whole W, let's just keep this frozen and instead add some delta W and only fine-tune that. Because mathematically speaking, it's just the same thing, right? Once we train this delta W, at inference time, I can just simply add this delta W to W, and I have a new W matrix that works as expected. So why we just do this? Because this is where LoRA comes from. LoRA says once we have this delta W, let's just say it is a 200 by 200 matrix. That means I have 40,000 parameters. But one thing I can do is that I can factorize this matrix into a matrix B, let's just say 200 by 2, multiplied by another matrix 2 times 200. And the multiplication of this B and A is exactly the same shape as delta W, but now we have 400 parameters for B and 400 parameters for A. But why this should work? If you know linear algebra, we have a concept called rank. And rank means how many columns that we can have to be linearly independent. And by linearly independent, I mean we cannot represent it by a combination of other columns. For example, if we are in a 3D dimensional having x, y, and z, we can say that x, y, and z are linearly independent because they cannot be represented by the other two. But the vector u can be represented by a combination of x and y and z. Like I can say u is 3 times x plus 2 times y plus 4 times z. But without having any u and by only having the 3x and y and z, I cannot represent any of them by the other two. And in a matrix like delta W, we can say that we are having 200 columns, meaning that we are having 200 different vectors. But some of them can be represented by a combination of the others, and we don't know that. So this rank is some hyperparameter that I set it here to be 2, and meaning that out of these 200 vectors, I only select 2 of them. So I have in the matrix B 2 columns, each are 200 dimensional vector. And from these 2 vector, I can represent all the other 200 vectors that I have in delta W. And how can I represent them? By some linear combinations that the coefficients belong to this matrix A. So that means like if you look at the first column of this matrix A, it is just having 2 values, right? Let's just say it A and B. That means if I multiply it, the first column of this matrix B by A and the second column by B, then I have the first column of delta W. And similarly, I can do it for the second column of A and do the same combination and have the second column of delta W and do it so on and so forth until I make the whole delta W. But in practice, we don't know that how many of these columns can be represented by the others, so we set it as a hyperparameter. And that hyperparameter depends on how much changes we want to perform. Like initially, if we are having a text and we want to fine-tune the model to also output a text that is very similar, then the rank could be assigned to be a very low value, like even 2 or 3 or 4. But in case that we are doing a lot of differences, like we are converting from text to this human pose, which are even in different modalities, then we need to have a rank that is higher. And how can we initialize this matrix A and B? We set the value of this matrix B initially to be 0 and A as a normal distribution with 0 mean and some standard deviation sigma. But there's one thing I didn't tell you. Based on my explanation, I can substitute this delta W by BA and I have something like this. That H is some initial W, which is frozen, plus B times A, which we need to train them, and some input X. But in practice, what they implement is not this, and instead they have some additional scalar alpha divided by rank. But why do we need to have this scalar factor? Because as I increase the rank, the more parameters I change. And by changing the more parameters, it is more likely for me to overfit. So by having this R in denominator, I say make these changes smaller and smaller as I increase the rank, which kind of makes sense. That means we are having the less chance to overfit. But what about this alpha? This alpha is another hyperparameter that we set to say how much change that I'm willing to have. So if I want to have a significant change, like the scenario that we are having here, we need to have an alpha that is higher, usually higher than the denominator. But in case that I want to preserve the information that I already have in the large language model, then I set this alpha to be a small value. That means I want to change only a bit of information, and I want to keep this large language model for the initial task as powerful as is. So for this PoseGPT, they set the value of R to be 128. That means we're having high rank changes because we want to change from text to another modality, and also alpha to be 256. That means we want to have a significant change. So okay, enough of this LoRA. Let's just come back to the PoseGPT. So the other question we can ask is how to construct data for training, which I believe it's a very important part of these LLM papers. One of the contributions that they have is that they just have a new idea of generating this new training data. Because other than that, the LLMs that they are using are very alike, and there isn't much contribution on that. So the first way of generating training data is for the task of text-to-pose generation. So a user gives some description and asks like, can you give me the simple pose of this person? And then the LLM has to answer something like, sure, it is this pose token. And then this pose token goes to a projection and then simple model, and we have the output 3D pose. But if I give it only this description and always give it something like, can you give the simple pose of this person? Then it doesn't have any diversity, right? And likewise for the output, it shouldn't be always like, sure, it is pose. We need to have some diversity in both the input and output. And for that, this paper also uses a different type of inputs. Like all of them are requesting the same thing, but the description is put in different areas and the request has a diversity. And likewise, we can do the same thing for the output. So it sometimes can say it is pose, sometimes can just give must the pose, and the other things as well. So this is for the text to pose generation. But another task that we also need to have is to interpret the images, and that is done by human pose estimation. So for this task, the way that they generated the data is that the user asks something like an image, and then they can ask, can you provide a simple pose of this person in the center of this image? And then the LLM says, sure, the simple pose of this person is, and then they give the pose token. And likewise for the input, we need to have more diversity, so they have different way of requesting it. And the final thing that we need for the training is multimodal instruction following. So the LLM they are using is called Lava version 1.5 that I already mentioned, but that model is specifically designed to answer some questions from the image that you ask. But if I train that only for the task of text-to-pose generation and human pose estimation, then it might forget the information it already has, the thing that we even need it. So just to preserve that information, they also use this Lava version 1.5 MEX 665K dataset that has a bunch of images and questions and answers just to preserve that ability. So okay, we can have these training data and then train the model with the loss function I already mentioned, but once we trained it, we can evaluate it for both this text-to-pose generation task and human pose estimation task, but in addition, we can evaluate it on these new benchmarks that they proposed. Like one of it is speculative pose generation. So the way that we need to evaluate for this task, just note that we only evaluate, not train. We ask a model something like an implicit description and can you give the simple pose of this person? And then the model says, sure, it is the pose. So what is this implicit description? It can be something like, the man is proposing marriage. What pose might he be in? Without even including this in training, since the model already has some word knowledge about marriage and what happens when a man proposes, the model should answer this question. But how can we generate this type of data for evaluation? They relied on a PoseScript dataset. So a PoseScript dataset comes from the PoseScript model that is originally developed for text to motion and motion to text. But this dataset, when you look at the text, they are very explicit. But we want to have some implicit descriptions. So they relied on GPT-4 and they gave these explicit pose descriptions, and as the output they have some implicit pose descriptions that we can use. And what about the result? We can have this prompt that the person could be proposing marriage, traditionally done by kneeling on the knee to signify commitment and respect. We can see that GPT-4 with DALL-E can successfully generate an image in a completely different modality that is exactly the same thing that we want. And likewise, PoseGPT can generate a 3D pose from this proposing marriage. But PoseScript, since it doesn't have the ability to understand this proposing marriage, then it generates something that is not reasonable. And likewise, we can ask like the person appears to be searching for something on the ground. And we can see that GPT-4 with DALL-E generate exactly like we want. PoseGPT also generates something that we want because it again just tries to search something on the ground. But PoseScript is not as accurate as we expect. And if you want to quantitatively compare PoseScript with PoseGPT, we can see this table that it has two columns. The first column is PoseScript, which is for the PoseScript dataset, is a kind of a traditional poses generation. And the right column is for this speculative pose generation benchmark that is newly proposed. And the metric used is recall rate. P2T stands for pose to text, and T2P stands for text to pose. We can see that the PoseScript can actually outperform PoseGPT on this PoseScript benchmark. But for this SPG benchmark that we have some implicit request, PoseGPT outputs something that's more reasonable. The other evaluation benchmark is reasoning-based pose estimation, that the user give an image and describe the person, and then it asks like, can you give me the simple pose of this person? And then the LLM says, sure, it is pose. And the description of the person could be like the man with black hair, the woman near the stairs. So this is what the others model for human pose estimation cannot answer, because they don't know what is the black hair or what is this stair. But for the generating the evaluation dataset, they relied on 3DPW dataset. They extracted 50 images that they have multiple persons in it. Then they use VIT pose to estimate some 2D poses, and then they added these 2D pose key points and the bones to this image, and then they give it to GPT-4 to describe the person behavior, shape, outfit, pose, and summary. So a question you might ask is that why do we need some VIT pose to 2D pose estimation? The answer is because when you usually use GPT-4 to describe what's happening for a specific person in an image, it usually mixes the left part and right part of the human body for some reason. So just to mitigate that issue, they used a VIT pose, and for the right hand side, they used some red key points, and for the left hand side, they're using some green key points. And explicitly in the prompt, they say, I already did that for you. The right side is denoted by red, the left side denoted by the green. And this way they kind of assessed this GPT-4, and they can have a better person description. And we can see some results here. Like we can have an image with two people in it in the foreground and the other two in the background, but we can only ask, like, give some descriptions of the person who is sitting and ask it to just estimate some simple pose. And we can see that PoseGPT does it very well. But for the lava, we can see that one of it has -s at the end, the other has -p at the end. For -s, the thing that they do is that they ask lava to generate some key points. And once it is generated, they try to fit the simplified model to these key points. So from some key points to 3D mesh. And what about -p? They ask lava to describe this pose. And once it is described, they use PoseScript to generate it. And of course, we cannot describe any pose in a text in a very clear manner to explicitly match the image. So we can see that this -p results is not very good. But on the right side, we can see HMR version 2 and a spin that they're specifically designed to do this human pose estimation. And remarkably, PoseGPT even is performing better here than a spin. Another example could be something like this, that we can say that we are interested in the man with the long hair looking towards his companion who is climbing the stairs. He's standing upright on the step. And we can see that once this description is given, PoseGPT generates something that is kinda even more accurate than these HMR2 and a spin. But I think the reason why it outperforms the other models is because we are giving it some sort of guidance of this pose. Like we are explicitly saying that he is standing upright. The thing that the HMR2, even though it is very accurate on a usual task, for this specific example, once we crop the image from the and we ask to estimate this person, it cannot really estimate it because it is not very clear because of the lighting issues or anything else. But for PoseGPT, since we already said it is standing upright, it doesn't make those mistakes. And for human pose estimation directly from the image, we can see that PoseGPT in general cannot be as accurate as the other models like HMR2 that is specifically designed for this task. But Lava-S or -P and even GPT-4-S-P, none of them can be as accurate as PoseGPT because, I mean, -P to me is not even fair just to ask some description from this and then ask some PoseScript to generate it. But if PoseScript is not accurate to estimate based on that description, and GPT-4 did its job very good, but we can see that for GPT-4-S they are more reasonable, but again they are not as accurate as PoseGPT. And to quantitatively compare it, we can see that for both different datasets like Human 3.6M and 3DPW, they have reported different metrics like mean per joint position error, or doing it after aligning it with ground truth. It is having always less errors than mean per joint position error, and mean per joint rotation error. So we can see that on comparing to the classic models specifically designed to do this human pose estimation, they are not as good, none of them. But PoseGPT is way better than the other models because they are not even trained for this purpose. But for reasoning-based pose estimation benchmark, that we give some text description in addition to the image and we ask them to kind of estimate it, we see that they're reporting three different numbers. The first one is mean per joint position, the second one is after alignment, and their last one is mean per joint rotation error. But interestingly, PoseGPT, once it's having the alignment with the ground truth, then it is having less error than HMR version 2. Even for the case that the description is only about behavior and shape and nothing about pose, which is kind of interesting. But yeah, that's all the thing that matters about this PoseGPT. If you enjoyed watching this video, don't forget to like and subscribe. And until the next video, goodbye.